Okay. This is Math 150, lecture 11. So what we're going to be doing today is the cross product. As I just mentioned before class, for the homework that's due on Friday, you can choose any one problem not to do. So if you do it, it's not going to be graded. You're still responsible for all the material, but you can do one less problem. There's also the snowman, snow person, snow creature exemption. If you have never built one or have a friend who has never built one, take advantage of the weather, send me a photo. Okay, so there's a lot of ways we can talk about the cross product. I've chosen this one. So if I give you two vectors A and B, then the cross product is defined as follows. I love this because when you look at this, your mouth should be open and you should be scratching your head going, why the hell would we want to look at this? This is a perfectly fine definition. I give you two objects A and B. There's the cross product. There's a lot of questions, why would we define something like this? What kind of properties does it have? So one of the more interesting properties is, with a little bit of calculation, we can show A cross B is perpendicular to both A and B. So if I have the vector A in this direction and the vector B in this direction, then the vector A cross B is going to be perpendicular to them. And so it's going to be forming two right angles. Does anybody know how we might be able to prove that A cross B is perpendicular to both A and B? How could we prove that? Yeah, just take the dot product. Somebody tells you that it's perpendicular. Well, we can just compute by the dot product. So the proof, show A cross B dotted with A is 0. And which 0 is this? Is it 0 the number or 0 the vector? When I take the dot product, do I get a vector or do I get a number? I get a number. Is 0 the number? And of course, similarly, you can show that if you take the dot product with B, that it's 0. This is a proof of just brute force algebra. It's very unenlightening. You have no idea why it's true. You just do the calculation, and at the end of the day, you see that it works out. We can define almost anything we want. The question is, when is the definition going to be useful? So this has lots of applications in physics. One of the big questions you want to ask is, when you look at this, is there a way to generalize this to higher dimensions? It turns out that the cross product really only exists in three-dimensional space. Now, where does two-dimensional space live? Two-dimensional space lives in three-dimensional space. We can use the cross product in 2 dimensions by just letting A3 and B3 equal 0. So even though we initially defined the cross product for vectors in R3, we could still define the cross product for vectors in R2. Just imagine that they live in R3 with the third component 0. But we don't have a nice generalization to R4 that's going to have the properties we want. One of the things that's nice is in 3 dimensions, if I give you A and B, and I look at all combinations of A and B, this is a plane. So we talked about equations of a plane. These are my 2 directions. So if I look at all multiples of A plus all multiples of B, starting at some fixed point, that's going to be a plane. A cross B is my 3rd direction. It's perpendicular to them. You could actually use this to get a normal direction. So if I wanted a plane where the directions are given by A and B, if I calculate A cross B, I can use that as the normal to the plane. If we start to go in 4 dimensions, all of a sudden, if I give you 2 vectors and I ask you, what's the direction that's perpendicular? Well, if it's a 4-dimensional space and I give you 2 directions, how many more directions are left? So 4-dimensional space, I give you 2 directions. How many directions are left? 2. And so I can't talk about the direction that's left over. But in 3-dimensional space, if I give you A and B aren't in the same direction, they give you a plane. There's a unique 3rd direction I can move in. You should have read the book and looked at a lot of the different properties. So the first is, how many of you remember determinants, maybe Cramer's rule from Algebra 2? I'm really terrified of where Algebra 2 is after years of the pandemic response. These are ways to solve systems of equations. We're not going to do too much with determinants. Once you take linear algebra, which would be wonderful if you had known that now, but given that it's the sequel class, it's unreasonable to expect you to know linear algebra. It makes a lot of these calculations easier. And so again, I'm just in the mood to define things today. And we can define the determinant of a 2x2 matrix to be A11, A22 minus A12, A21. Or as we sometimes write the matrices, A, B, C, D, this would be, the determinant of the matrix A is AD minus BC, where A is the matrix A, B, C, D. And we use parentheses to denote the matrix. We use straight lines to denote the determinant. So the determinant could be a negative number, could be a positive number. The determinant has a lot of properties. It turns out that the determinant gives you the area of the parallelogram generated by these vectors. There is a definition for the determinant of a 3x3 matrix, and that's going to give you the volume of the parallel pipehead spanned by the three vectors. And this is called expansion by minors. We're not going to do too much with this. The next one, here is an interesting way to define the cross product. So remember, I is the unit vector 1, 0, 0, j is the unit vector 0, 1, 0, and k is the unit vector 0, 0, 1. So the one unit x direction, one unit y direction, one unit z direction. And we define v cross w to be take the determinant of this matrix. This is really illegal. Over here, when we have the determinant of a 3x3 matrix, again, just using the definition, I'm putting in 9 numbers. And now what I'm deciding for the next one is, well, I'm not really going to use 9 numbers. I'm going to use 3 vectors for the first row, and then I'm going to use 6 numbers for the remaining 2 rows. I'm just treating this as a mnemonic. This is a nice way to remember what v cross w is when I expand it out, this is going to become, let's see if I can write small enough. Actually, I can zoom in, good. So I can write v2 w3 minus v3 w2. And then over here, this would be v1 w3 minus v3 w1. And then over here, this would be v1 w2 minus v2 w1. Okay. And so I can expand these out using my rules. And this is just a mnemonic for remembering what the formula is for the cross product. And again, going back, if I have my vectors A and B rather than B and W, not a big deal. It's A2B3 minus A3B2. Okay. A3B1 minus A1B3, A1B2 minus A2B1. There seems to be a really nice pattern here. 2, 3, then 3, 2. 3, 1, then 1, 3, 1, 2, then 2, 1. Now notice here I have all positive signs. The first thing is always positive. If you look at the next page, it goes positive, then negative. Well, another way is if I don't want to have the negative, it would be the same as plus v3 w1 minus v1 w3. And so I write it in the opposite order so that I now have, it goes 2, 3, then 3, 1, then 1, 2. So we have this nice cyclic way. These are just ways to try to remember things. This is a little bit of an illegal formula, but it's a nice way to just remember what the answer is. Now, it turns out the cross product has a lot of nice properties. One is v cross w is orthogonal or perpendicular to v and w. And we can see this by just taking the dot product and just doing the calculation. That's just roll up your sleeves and do the algebra. It's not necessarily illuminating, but we can do that calculation. The next one is a little bit more interesting. V cross w has length of v, length of w, sine of theta. Well, again, whenever you see a formula, you want to ask, is it reasonable? So if I go back a page and I look at my formula for a cross b, if I triple a, what happens to each of these products? If I triple a, what happens to each of those products? They get tripled. And what about the middle component? What happens if I triple A? It triples. And the final one, it triples. So we see that whatever the length of this vector is, if I triple the length of A, I triple the length of this vector. So I know the length of the cross product has to be related to the length of A. Similarly, it's going to be related to the length of B. And so when I look at this formula, that it's the length of V, length of W times the sine of theta, I have absolutely no idea. But I do understand that it has to be related to the length of V times the length of W. I can do a little bit more. I can show you that the sine of theta is at least reasonable. This should look like gobbledygook paint. Can anybody give me two vectors A and B where it will be easy to calculate their cross product? Yeah. Two vectors A, B.
1, 1, 1.
And?
2, 2, 2.
Okay, now 2, 2, 2 is in the same direction as 1, 1, 1. So do 1, 1, 1 and 1, 1, 1. So what would be the cross product of 1, 1, 1 and 1, 1, 1? 0. What would be the cross product of any vector with itself? 0. What is the angle a vector makes with itself? Well, theta would be 0. What's the sine of 0? 0. So the fact that I have a sine of 0 is at least reasonable. I know the cross product has to vanish when the vectors are parallel. Okay, this works. Okay, so this is not a proof. The next part is that V cross W forms a right-hand system. Are there any students who are left-handed? Damn it, you're not supposed to be admitted. That's all right. How good is your right hand? You can write with it. Okay. So my son became a left-handed hitter because his favorite player was David Ortiz. And so when he was very young, he just mimicked David. And even though he is a righty, he's learned to do a lot of things lefty. This is notation. We get to choose which way we want to do things. And we've chosen to do the right-hand rule. You could, of course, do everything with the left hand. We've just normalized all the conventions like this. And if we take two vectors V and W, we put our fingers aligning with V, curling them towards W. And then our thumb, our right thumb, points in the direction of V cross W. If I tried to use my left hand, well, then that would be W cross V, that would be the opposite. So worst case scenario, you're off by a minus sign. Most of the time, it's not a huge deal if you're off by a minus sign, but you do have to be careful about this. Right? So when we're trying to figure out which way does V cross W point, it's normalized so that if I take my hand and curl it from V to W, my thumb is pointing in the direction of V cross W. So there's a lot of nice properties. The first, W cross V is negative V cross W. And again, this can be proven by brute force algebra. If I just change the roles of A and B, well, you can see that's going to multiply each of these by -1. So a lot of these results can be proven by just doing some algebra. And so if I change the roles of A and B, that's going to flip that. Okay, so W cross V is negative V cross W. V cross W is 0 if and only if W is in the same direction as V. So that's a little bit more interesting. It's clearly true that if W is in the same direction as V, then V cross W will be 0. Without loss of generality, we can always assume our two vectors have unit length if we want. We can always rescale by dividing the vector by its length. So if we want, we can assume V and W have unit length. So as a nice exercise, see if you can prove that if V is not in the same direction as W, then at least one of these expressions here has to be non-zero if V and W are not in the same direction. Okay, so that's a nice exercise to just see, can you just do that by algebra? The next one is lambda V cross W is V cross lambda W is lambda V cross W. Well, that makes sense. I'm basically just rescaling one of the vectors. And we've seen that the formula has to be proportional to the length of the vector. The last one is really interesting. What law is the last one? U plus V cross W is U cross W plus V cross W. Distributive. If I truly hated you, I could give you as a homework assignment, prove the distributive law. Right? Well, no, if I truly hated you, I give you something much, much worse than this. This isn't that bad. You plug in U, you plug in V, you plug in W, and you just expand. And at the end of the day, after the algebra settles, you see that they're the same. Or even better, you use a symbolic program like Mathematica and have Mathematica just expand it out and subtract the left-hand side from the right-hand side and just show that everything is the same. So by brute force algebra, we can prove the distributive law. Okay? So if we prove things by the distributive law, this actually gives us some interesting ways and options to try to calculate the cross product. Because what we could do now is we could say, let's calculate the most important cross products. What is I cross I? So what would I cross I equal? 0. 0 the number or 0 the vector? Sorry? It's 0 the vector. The cross product gives you a vector. It's 0 the vector. And similarly, we know J cross J is going to be 0, and we know K cross K is going to be 0. Now the next one is I cross J. So that's going to be K. What about J cross I? Negative K. And now if we do I cross K, so we've got the x-axis curling up to the z-axis. So is it going to be J or negative J? I think it's going to be negative J. And we can go back and we can check, if we go back to the definition, if we do I cross K, so we can do this as an example, I cross K is going to be 1, 0, 0 cross 0, 0, 1. So the first component is A2, B3. Well, A2 is 0, so I don't have to worry about that. A3 is 0. So I know the first component is 0. For the second one, it's A3, B1, that's 0, minus A1, B3. Oh, A1, B3, that's a negative 1. And the last one is B2 and B1, which are both 0. So it's just going to be negative J. Okay, so now we know I cross K is negative J. So what would K cross I be? So that would be J. So we're almost done. We now need J cross K. So I take so here's my X, Y, Z coming up. I take the Y crossing into Z. My thumb's pointing in the positive X direction. So J cross K would be I, and then K cross J would be minus I. Okay. So I'm getting these by just, using the definition of the cross product in some special cases. I could go another route. I could start off with, this is my definition of the cross product of these fundamental directions. And then I'm going to define the cross product using the distributive law and just show that everything works out. So if I wanted to give you, say, A1, A2, A3 cross B1, B2, B3, this would be A1I plus A2J plus A3K cross B1I plus B2J plus B3K. And now when I go through this, I've got 9 terms. Not coincidentally, the first half of the page tells us how to handle each of those 9 terms. So if I want to get something in the I direction, which are the only ones here that can give me something in the I direction? J times K, and what else? K times J. So the first is the K times J. So here's my K, here's my J. That's going to give me A3, B2. And then the other one would be J times K, which would give me a minus sign because that's going to give me a minus I, right? So I will get minus, and then it'll be A2, B3, I hat, and so on. So by using the distributive rule, if I just set off with my definition of the cross product like this and say I want the cross product to satisfy the distributive rule and all these other stuff, it forces this definition on me. All right, so is everybody okay with at least the definition of the cross product and how you just formally work with it? Now let's try to motivate why would we do this. So hopefully you understand that area is something we care about. You know, I teach probability often. I do a lot of work in the subject. Areas under curves can often give you probabilities of events. These are things that are very valuable to figure out. Let's say I give you, here is 2 different vectors. Actually, let's make this one a little shorter. And then what I can do is I can look at the parallelogram spanned by them. And I want to calculate what is the area. And there's actually 2 different ways of doing this. So I can give you the matrix A, B, C, D. And so I'll call this point AB, this point CD. What would this green point be over here? What would be the coordinates of that point? A plus C, B plus D. And I want to find the area of this parallelogram. If I rotate my coordinate axis, does that change the area of the parallelogram? That's one of our assumptions from geometry. So if you've ever really rolled up your sleeves and dived into Euclid, if I translate a line segment, and for those of you who are taking physics, it's translating, then I'm putting it back down. I'm not worrying about relativistic effects, just physically moving it, putting it back at rest. Its length should not change just because I've moved where it's located. If I rotate my coordinate axes, if I rotate my parallelogram, that shouldn't change its area. One of the things you could do in linear algebra is you could say, hey, without loss of generality, what would be a really nice direction for one of my 2 vectors? If you could choose one of your vectors, which direction would you point it? There's 2 natural choices. So you want to choose, I'm giving you a vector. What direction would you take your initial vector to be? The x-axis. And if you wanted to be a little bit different, instead of the x-axis, you could choose, yeah, I mean, crazy, but you could do the y. But without loss of generality, let's assume the first vector is in the direction of the x-axis. And what you can do is you can prove linear algebra results that show that the determinant or the cross product of all these different things are unchanged under rotations. And without loss of generality, if I want to do my algebra, I can choose the coordinate system where the first vector is just in that direction. It makes a lot of the calculations a lot easier. When you're trying to think about what is the dot product, well, if one of them is in the direction of the x-axis, side, dot product. So here's my coordinate axes. Imagine one vector is in the x-axis direction, and I'll call that u. And here's my other vector, v. So v will be maybe x comma y. U will be maybe a comma 0. And now, what is, let me change which one is, I'll make this one V and the other one U. Here's U, here's V. So if I look at U dot V, that's just going to be X times A plus Y times 0 is just X times A. Well, if we think about what's going on, if I want to look at how much of this vector is coming down in this direction, right? What would that amount be? Well, that's just going to be its X coordinate. And so when I'm trying to do my projections, your X times A is a very natural thing. It's the length of the U vector in the V direction times the length of the V vector. So let's go back over here now to trying to find the area of a parallelogram. So if I give you a parallelogram, how would you find the area of a parallelogram? Anybody remember the formula for the area of a parallelogram? Which, the two sides? If it's a rectangle, you can multiply the two sides. The length, okay, so I need the height. So if I can calculate the height, and this is the base, the area is base times height. Okay, well, the base is just going to be the length of AB. And the height, let's do it slowly. So base is the length of the vector AB, right? And the height is, let's see, if I call this angle here theta, it's going to be the length of CD times the cosine of theta. I'm sorry, not the cosine of theta, times the sine of theta, right? Because if I have a right triangle, here, my hypotenuse has the length of CD. And so the length of this height here is just going to be the hypotenuse times the sine of the angle. So I get that the area is A squared plus B squared to the 1/2, C squared plus D squared to the 1/2 times the, oh crap. I was wondering why the word area vanished. I somehow shifted to converting to text. Okay, so area is A squared plus B squared to the 1/2, C squared plus D squared to the 1/2 sine of theta. Does anybody here like square roots? Right. How can we get rid of the square roots? Yeah, so let's look at the area squared. Area squared equals A squared plus B squared times C squared plus D squared times sine squared theta. All right. I'm saying that somehow this should be related to the cross product. I said the cross product is somehow related to the area. The cross product somehow has a sine of theta. Have we seen anything that has a theta involved in it in this class yet, when we've been doing vectors? Where have we seen something involving a theta? I'm sorry? The vector projection, then what are the vector projections coming from? They're coming from the, what operation are we using? The dot product. Now, does the dot product give us a sine of theta? It gives us a cosine of theta. Damn it. Do we know how to convert from sine squared to cosine squared? Yes. So now we use sine squared of theta is 1 minus cosine squared of theta. And so we get the area squared is a squared plus b squared, c squared plus d squared, and then 1 minus cosine squared of theta. But we know AB dotted with CD is equal to the length of the vector AB times the length of the vector CD times the cosine of the angle. So AC plus BD squared is A squared plus B squared, C squared plus D squared, cosine squared theta. Right? I've just squared both sides. Could I use this to solve for cosine squared and substitute? Yeah. But there's no need to do that. Notice that cosine squared is actually hit by a squared plus b squared times c squared plus d squared. Oh, that's exactly what I have here. There's no need to solve for cosine squared and plug that in. It's not cosine squared that I want. I actually want this whole thing. So when I substitute, I get area squared is the first, everything hits the 1. So I have a squared plus b squared, c squared plus d squared minus, and now I'm going to get AC plus BD squared. Okay. So if we expand things out, we get a squared c squared plus a squared d squared plus b squared c squared plus b squared d squared minus, then when we expand everything out, everything's going to have a minus sign. I'm going to write the minus stuff in the next line. It's going to be a minus a squared c squared minus a b squared d squared, right? And then I have minus twice the cost, or minus 2a b c d. So when the dust settles, I get that the area squared is a squared d squared minus 2a b c d plus b squared c squared, which is ad minus bc squared. So the area is ad minus bc, which is the determinant of our matrix. Okay, it's not fun, but we only have to do this algebra once in our life. And we now see that the determinant actually represents something that's geometrically important. So, I initially gave you a bunch of, facts. Let's define the determinant of this 2 by 2 matrix to be, AD minus BC. It turns out that that's useful. That gives you the area of the parallelogram spanned by these two vectors. It is not at all clear when you look at this that that's what you're going to get at the end of the day. But when the dust settles, that's what you get. And notice that when we're doing all these calculations, if I give you the vector AB0 cross CD0, and I want to calculate the cross product. The way we're told to do this is to do the 3 by 3 determinants. We do I, J, K, and then we put the first vector in A, B, C, AB0. And then the second one is going to be C, D0. And we're told what the expansion is. How many of you have not seen 3 by 3 determinants? Okay. I will show you a trick that only works for 3x3 determinants. What you do is you repeat the first two rows. The first two columns. And the rule is the following. You go diagonally down like this, and these all have a plus sign. And then I need another color. If I go then in this direction, these three all have a minus sign. So this is a nice way to just remember what the determinant is. So what I would get in this situation is I would get I times B times 0 plus J times 0 times C plus K A times D. And now I get the minus ones. I'll get minus K C times B. Then I'll get minus I times D times 0, and then minus J 0 times A. And so when the dust settles, the only terms that survive is this one and this one, and I get AD minus BC in the K direction. So what that's saying is if I take my vector here, AB, and I take my vector here, CD, and I take their cross product, this is the cross product, AB cross CD. And here, because my third component is 0, my vectors actually live in the plane. They live in the standard XY plane. This is true in more generality. And again, when you take linear algebra, it's a lot easier to do these calculations. But the cross product, at least in the special case of the plane, is giving the area. So if I give you two vectors in the plane and I calculate the cross product, I have proven that it's the area. And I've proven that it's equal to the length of one times the length of the other times the sine. Because we know that it's equal to the length of the first times the length of the second times the sine. But after doing more algebra, we eventually showed that it also equals the cross product, the AD minus BC, which is what we just got over here. So I've shown that if I live in the plane, it is length of V, length of W, sine of angle. It's the area. What I have not done is shown that this is also true in 3 dimensions. I have no desire to do that. You have no desire to see me do that. If I'm wrong, I'm happy to meet with you privately, roll up my sleeves and do the algebra. I think for first class, this is enough detail. We've done it in the plane in great, great rigor. Nothing was hand waved in the plane. In higher dimensions, you just have to go through. I actually think that this is a much better result to do once you know linear algebra, and you can talk about, well, if I can show that these quantities are unchanged under rotations, well then without loss of generality, why don't I choose my XY axes so that your V and W live in the XY plane, make life easy, do the analysis there, and then rotate backwards at the end of the day. So this is leading up to, in the very near future, we're going to be talking about different coordinate systems, do things in the proper coordinate system. If you're walking in New York and you're giving measurements other than east, west, north, south, and Manhattan, you have issues. That's the natural system to use when you're walking there. Okay, so any questions here about how we calculate the determinant? So again, there's just a couple of formulas you just need to memorize. So here is the formula that it's IJK, and it's this expansion by minus. Okay, there we go. So I take I, and then it's the determinant of this. Then I take J, and it's the negative determinant. And what happens is when you choose each one, you delete everything else in that row and column. And then when I get to K, I delete everything in the row and column, and that's where I get this. It alternates in sign. And so that's what makes things a little bit tricky, is you have to remember the sign there. There are just some things you have to memorize. You can do it like that. You can memorize the formula here. It's A, B, 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 A, B. Okay. Then just goes 2, 3, 3, 2. 3, 1, 1, 3. Then 1, 2, 2, 1. That's not that bad. Or if you want to memorize as little as possible, you can just memorize these. 3 of the things are 0, and then 3 of the things are the negative of the other ones. So you just have to remember I cross J is K, K cross I. It's that cyclic order. I go from I to J, it's going to be positive. I go from J to K, it's going to be positive. I go from K to I, it's going to be positive. If I do things in the opposite order, I get a minus sign. So here, unfortunately, order matters. This is not the same as normal multiplication. Okay. And then again, a lot of these properties can be proven by your brute force analysis. Always keep track of, do I have a vector or do I have a number? And so think, if I'm taking the cross product gives back a vector. If I take a dot product, I get a number. Try to recognize patterns. Where have we seen something involving an angle? We've seen it with the dot product. So when I'm doing the analysis here and I see the sine of theta, I'm immediately thinking, oh, I know how to deal with this. I somehow convert it to a cosine and I know what cosine is. And then I just have to do a bunch of algebra. And when the dust settles, I now get AD minus BC. And so you can talk about what happens in higher dimensions. The real geometric interpretation of a determinant is it's the volume of the parallelogram, parallel pipette, whatever dimensional space you're in. If I give you 2 vectors that are in the same direction, what's the area of the parallelogram that they span? So it'd be 0. If I give you 3 vectors that lie in a plane, what's the volume of the parallel pipette? 0. And so a lot of these formulas, reduce in the special case that, if I have something like this, it's a degenerate object, the answer is going to just be 0. We have nice ways to tell if 2 things are perpendicular. We take the dot product and is it 0? So we could actually see that this definition is going to give us something perpendicular to A cross B. This is a really nice feature of 3-dimensional space. What is Sherlock Holmes' most famous saying? Ooh. That's not the one I was thinking of, but that might actually be the one I was thinking of. So I will have to give you cultural credit for that. What's his then maybe second most famous? His advice. Elementary, my dear Watson. His advice in solving things. When you eliminate the impossible, whatever remains, however unlikely or improbable, must be true. If we have a 3-dimensional space, and I know I'm perpendicular to 2 of the directions, there's only 1 direction that's left. That's one of the nice things about the cross product. Oh, I've given you 2 directions. I know where I have to live. I've got to live like this. It's a nice advantage we have working in 2 dimensions that we're not going to have in general. And so if I want to do the equation of a plane, so I want equation of a plane through P naught and containing directions V and W. So again, here's my base. Here's my point P naught. Here are my 2 directions, say V and W. And then there's going to be the plane. So we talked about one way to do it. I could say it's all points P that are equal to P naught plus TV plus SW. And that's a nice 2-dimensional space. I could also calculate, I still have purple available. I could also calculate the normal to the plane. And it's all points such that P minus P naught is perpendicular to the plane. I'm sorry, P minus P naught is going to be in the plane. It's got to be perpendicular to the normal direction. So what does it mean to be perpendicular to the normal direction? The dot product is 0. 0 the number or 0 the vector? 0 the number. So I can write this as, P dot n equals, P naught dot n, or if n equals ABC and P is XYZ, I'll get AX plus BY plus CZ equals D, which is my P naught dot n. If I wanted a parallel plane, I could just shift everything up. I could have a different base point. And all that's going to do is that's going to just change the value of D over here. It's like having two parallel lines. I can have two parallel planes. I need, however, the normal vector. I need a vector that's perpendicular to V and W. Can somebody give me a vector perpendicular to V and W? V cross W. So one thing is to do n is equal to V cross W. I could also do n is V cross W, and I could rescale it and divide by the length of V cross W. And that would be a unit vector. And we sometimes use a hat to denote that it's a unit vector, so you can quickly look down. Well, it doesn't really matter if I use V cross W or a normalized V cross W. Let's say the length of n is 5. Well, if I normalize this, I would divide the left-hand side by 5. I would divide the right-hand side by 5. It's the same equation. Which is more convenient to look at, V cross W or V cross W divided by the length of V cross W? Yeah, V cross W. Does anybody really want to calculate the length of V cross W and divide by it? No. If I'm just trying to write down the equation, this will work. If I then need to do some calculations with it, I might want things to be as simple as possible. Okay, what was your question on scaling? I wanted to make sure we left some time for that.
That was a question about projection.
Oh, okay. Okay, so is this how to calculate a projection, or?
Like, kind of, why do you do it? Was my question.
Okay, so why do we care about projections? So when we're going to get further in, so projections. So let's say we have, some surface like this. Okay, so we have some surface, and I'm at some point on the surface. And what I can do is I can look at the direction I'm moving. So at any given instant, I'm moving tangent to the surface. This is very similar to, you always go back to, calculus, to, I have some curve. And, I have at some point, I then have the tangent line at that point. And I can ask, how do things change? So it turns out what you can do is you can have a normal to your surface. So maybe I've lost my purple. So I could have my normal direction to the surface over here. And now what I might have is I might have some function that I care about. And I might ask, how is the function changing? And so it turns out that what we can do is we can associate a vector called the gradient of f. It's a df dx, df dy, df dz. So these are the partial derivatives we talked about earlier. And so what this means is df dx is take the derivative of f with respect to x and keep y and z constant. Then the next is take the derivative with respect to y, keep x and z constant. And if I put them together, this is going to be a vector of partial derivatives. And it turns out this gives me a lot of information about how things are changing. And what I'm going to care about for some applications, do we have any econ perspective majors here? All right, so this will come up in some of economics, is I might care what component of this derivative change vector is in the direction I'm flowing on the surface versus what direction is perpendicular. So the part of it that's perpendicular is not going to matter at all in terms of how I'm changing. I'm going to care about its projection down here. And that's one of the reasons why we're going to care about projections. We're not going to need to use all the fancy formulas that they have. It's good to know fancy formulas exist. You've seen them, but all we're going to really care about is just, does the gradient of f have a component in here? If yes, if I flow in this direction, f increases. If I flow backwards, f increases. If my component is 0, if there's no projection down here, it's a candidate for maximum or minimum. So it's a really good question as to why do we care about this? Why are we doing all this? It's leading to applications in calculus to optimization. All right, so this is a point to stop for today. Remember, you can choose any one homework problem that's due tomorrow, due Friday. To me, tomorrow is always next class, and not do that. Okay, so just choose any one problem and don't do that.